welcome to our point distribution webinar. Our speaker today is the Shujie Kang. She will tell us on the rank of from the University of Texas at Arlington, and she will tell us about the ranks of non-informationally complete POMs. Please, Shujie.
Thank you for introducing me, and thank everybody for coming, and thank the organizer for inviting me. Today I'm gonna talk about the ranks of non-informationally complete POEMs, which is a joint work with Seth Goldberger and Kazuo Kujo. So I believe that Kazuo have gave a talk on a related topic before. So this is a continuation on his talk. So I'll give some of the details that he did not have time to, and we'll explore more on this matter. Okay. So this POEMs is actually a term from quantum physics. So you might ask, why do I use these terms in a talk that faces more toward mathematics people? So the reason we are keeping this term is that we came up with this question when we were trying to learn more about the Donner's conjecture, which is on a certain type of POEMs. So that's why we keep this term. But for those who are not familiar, of course, the first thing I want to do is explain my title. What is POEMs, and what do we mean by informationally complete POEMs? So we start with what is a tight frame. So this is FONTF, but a finite tight frame is a frame with vectors, we call it phi of k, such that if for any vector in CD, we have the sum among all the absolute value square of the inner product between x and phi k is equal to some constant times the norm of x squared. Okay, and this rank 1 POEMs, which is short for positive operator valued measure, actually correspond to the concept of tight frames because of this feature that tight frames have. So for the convenience, in this talk, we'll only care about the tight frames which have unit term. So those type of frames we call FONTF, that is a finite unit norm tight frames. So for FONTFs, we know what the constant is that we need to multiply x, the norm of x squared by, which is the number of vectors in the frame over the dimension it is in. Okay. So from now on, just in this talk, we'll use FONTF and POEMs interchangeably. Okay. That's about the terms. Okay, so we consider the operators, we call them pi of k, which is equal to phi of k times the transpose, or the transpose conjugate of phi of k. So the concept of informationally complete is based on this P. So we say that a POEM is informationally complete if the set of operators P is a spanning set for all the divided complex matrices. So by the definition of
Shujie, there's something strange happening with your sound right now. I don't know how we'd be able to fix it. It's coming in with the. Sorry, it's coming in with a decent bit of static. Sorry, there are dogs where I am.
Okay, but does anyone else have the same problem?
Yes, I do have some problem.
Yes, I think everybody. Yeah.
Do you want to maybe make sure to, I don't know, maybe close a few things, or maybe if you have any device like nearby that could.
Did you have the same problem when we were using Zoom chat before? Because let me look at I don't have anything else open.
It's probably your connection, I feel like.
Maybe. Yeah, let me know if it happens again.
Will do.
Okay. Right. So I was talking about POVMs and informationally complete POVM. Should I repeat it? All right, so basically, interchangeably we'll use POVMs. It means the same thing with FunTFs in this talk. Okay. And we'll consider the operators that consist of projections actually onto these vectors. So phi of k times phi of k star, and we call the collection P. Okay. So we say it is informationally complete if we have a spanning set for all the d by d matrices in complex space. So basically, right now I explain everything in the title. So the non-informationally complete POVMs are POVMs that do not form a spanning set. Right? Why are we looking at those? I'll explain later. And since we are talking about POVMs, there is a very interesting conjecture that a lot of people are working on that I want to mention, which is the Donner's conjecture. The Donner's conjecture is state that for any dimension that is greater than 2, then we can find this informationally complete POVMs with some extra property which is called symmetric with d square vectors in CD, where symmetric means that the angle between any of the operators phi k and pi of L, which we can define this inner product as the Hilbert-Schmidt inner product. So if all the inner products, the absolute value of inner products are the same for nk and L, then we say the POM is symmetric. So Donner's conjecture is still open in a lot of dimensions. They have people have an analytic construction for some of the dimensions, and they have numerical results for some of the dimensions. Okay. But that is so one natural candidate when people are trying to study about Donner's conjecture is the Gabor finite frame, okay? Because Gabor frames have n square vectors, d square vectors in CD. So it would be like a natural candidate when we're searching for those type of vectors. So I'll define the finite Gabor frame here. So given a unit vector G in CD, we call the collection of all the translation and modulation of the vector G, which we denote phi of G, to be a finite Gabor frame. So a finite Gabor frame in CD have d square vectors. So one thing about this frame being finite is that we know that all the finite Gabor frames are actually from TFs. So we know that there is a question, right, if we're dealing with Gabor systems in infinite dimensional spaces, then we do not know whether we have time frames. But since we are in finite dimensions, we have this nice property, right? So our question that we want to ask today, which is related to the conjecture, but not exactly the same, is that, okay, first question is that when is a Gabor POEMs informationally complete? In other words, can we fully characterize those type of vector G's such that it generate a informationally complete Gabor POEM? And the second question is that if we don't have a informationally complete POEM, then can we characterize the dimension of the subspace distance? So the answer to the first question, I believe Kazu also talked about in his talks, is yes, and we have the following result. Okay. So suppose we have a Gabor POEM in CD generated by a unit vector, and consider P the set of operators of G times of the GKL times star of GKL. And we call the gramming of P the matrix G. So we have the following. First one is about the structure and the spectrum of the gramming G. So G is itself a block circular matrix with circling blocks. And because of the structure it has, we can diagonalize it by the Kronecker product of two D by D DFT matrices. And we know that the eigenvalues of G are D times the absolute value square of inner product between actually two vectors in the Gabor frame. So I think I find this result interesting because this eigenvalues actually are equal to a constant times these actually are the entries of the Gramian matrix G. Okay. So since we know about the spectrum, if we want to know the rank of the Gramian G, then we just need to know how many non-zero entries are there in the set of eigenvalues. So that's why we have the second statement here. The rank of the Gramian G is equal to the number of non-zero entries among all the different inner products between G and GKL. So of course, if we want informationally complete POEMs, we will require all the inner product to be non-zero. And we also have a lower bound for the Gramian because we know the trace of G, right? We have one on the diagonal. So the trace of G is D squared. And we also know that the largest eigenvalue is D because we can take G, K and L both equal to 0. So combining those two, we can conclude that the rank of G is greater than or equal to D. Okay. So having this characterization, we want to mention that there are a lot of informationally complete POEMs. And in fact, we say that it has a generic property because of the following proposition, that if we are in any dimension that's higher than 2, then, well, first, of course, complete Gabor POMs exists in CD, and the set of all normalized vectors such that it generates a informationally complete POEM is open dense in the unit sphere in CD. Right. So to prove that, we will look at these this set in Zariski topology. So if we consider the complement of the set where one of the eigenvalues is 0, so we call the complement SKL, then this set is a open dense set in the unit sphere in the Zariski topology. And so since we know that the finite intersections of the intersection of all the non-empty open dense set is also non-empty open. So we can say the same thing about the collection of generators for all the informationally complete POEMs, because they are exactly at the intersection of all the set such that the eigenvalues are non-zero. Okay. And aside from that, we actually know that we can construct these generator unit vector G with any support whose cardinality is larger than DO2. So in other words, if we have a unit vector G such that the zero norm is greater than DO2, then it's possible that it can generate a informationally complete POEMs. So the proof for this result is actually similar with the previous one. So now we only consider the generator G, whose support is a subset of 1 through D. Now we can use the same idea that so if we consider the algebraic subvariety V of S of all the vectors with support S, then this set G such that it is with support S and the eigenvalues are non-zero is a non-empty open set in the Zariski topology. So again, with the same procedure, we know that their intersections, which is exactly the collection of all the informationally complete POEMs with support S, is also non-empty. Okay. All right. So that's about informationally complete POEMs. So the major part of this talk is going to be on the other part, which is the non-informationally complete POEMs. So what I'm going to do in the next two sections is that I'm going to make some observations and characterize part of the possible dimensions of the gramming G, and then I'll give some examples in certain dimensions and some examples in prime number dimensions in general. Okay, so before we characterize the rank of non-informationally complete POEMs, I would like to mention some of the what I call equivalence relations. So there are a few transformations that preserve the rank of the gramming G. So something that we can all think of, because the rank of G based on the number of zeros we have between the inner products. So if we multiply a phase in each term of G, it won't change the rank of the gramming. So similarly for additive translation and multiplicative translation. Right? And this is not all. So we have some more complex examples. For example, we can multiply by a quadratic phase to each of the term. So this examples, from this examples, I just want to show that there are many transformations that preserve the rank of gramming. And in the following, when I talk about up to this equivalence transformations or equivalent to some vector G, I mean, we consider all the vectors that can be obtained from these transformations are equivalent. Okay. So, right, starting with what we already know. So we mentioned that the rank of the gramming is greater than or equal to D. So the first thing we look at is when can it actually equal to D. So we have this theorem that up to all the transformation that preserve rank, including phase translation and quadratic transformations, a unit vector have rank D if and only if it have a certain periodic structure. That so for some kappa that's divisible by D. So GFI is a notation for the ith entry of this vector G. So GFI is equal to 1 if I is equivalent with 0 mod kappa and 0 everywhere else. So, like for example, if we're looking at dimension 4, then we can have k equals to 1 and 2. So when k is equal to 1, then we have 1, 1, 1, 1. And if kappa equals 2, we have 1, 0, 1, 0. Okay. So in particular, if we have a vector in CD whose 0 norm is equal to 1, then the rank of G is equal to D. And actually, I want to make more comment here, as if we have prime dimension. So for example, if D is a prime number, for example 7, then the only kappa that's divisible by that prime number is 1 and itself. So the only vector G that generates rank D gramming is either the vector 1, 0, 0, 0 or the vector with 1 at each position. So how do we prove this? Actually, we can prove this by using a Cauchy-Schwarz inequalities. So one direction of this, if and only if we can prove by some computation, right? That's the if part. So if we want to focus on the only if part, so now assume that we have a gramming G of rank D. Okay, then since we know that the largest eigenvalue is equal to D, then we can be sure that the the eigenvalue D is the only non-zero eigenvalues. Okay, so now suppose we have S equal to the support of G, and kappa be the smallest positive integers such that both I and kappa plus I is in the support S for any I. Okay, then this is actually the inner product between G and GKL, right? And we conclude that the eigenvalue is D times the inner product. So 1 is equal to the inner product itself. 1 is equal to that, and by Cauchy-Schwarz is less than or equal to the square root of this square sums, which is less or equal to 1 because each of the term have that property. So we have 1 on both sides. Now all the inequalities should be equalities here. So we conclude 2 things, right? So for the second inequality to be equal, right, we need both of these 2 terms equal to 1. Right? They're actually, so this is the norm of, this is less than or equal to the norm of G, and this is actually the same thing. So for that to be equal to 1, that means norm of G is equal to the absolute value square of each of the terms at I's position, where I and I plus kappa is both in S. So that means this is just everything. This includes everything. So we can conclude that we do have a periodic structure for G. So if I is in the support of G, then all the I plus kappa, I plus 2 kappa, etc. are in the support of G. Right. And for the first equality to hold, we want, right, G of I, we want G actually to be a scalar multiple of translation of G. Okay, so that means G at I plus kappas is equal to alpha times G of I for some constant alpha. Right? And so after the modulation by this phase, we get our result that G of I is equal to 1 when I is multiple of some kappa and 0 otherwise else. And then if we just normalize that vector, we get the only possibility that generates a grammine that's of rank T. Okay. All right. Okay. So for the other, when we want to characterize the generator G of grammine with other rank, I want to first quickly introduce the method we use, which involves the Fourier transform and the uncertainty inequalities. So basically, because the eigenvalues are just scalar, the eigenvalues are related to the inner product between G and GKL. So we can view this vector, right, which is a conjugate of the inner product between G and G0L through G d minus 1L as a Fourier transform of this vector, which we call WL. So WL is actually the term-wise multiplication or termwise product of the vector G and the conjugate of G translated by L. So since we can see that as Fourier transform of the vector WL, then we can use some uncertainty inequalities that's on the zero norm of WL and its Fourier transform to help us decide what is the rank of the gramming, since the rank of gramming should be equal to the sum of all the zero norm of this WL. Okay, so here are some of the simple and actually classic uncertain inequalities that are related to what we're doing today. So the first one works for any dimension D. So if we have a vector in CD that's non-zero, then the product of its zero norm and the zero norm of its Fourier transform is greater than or equal to D. Okay. And in addition, if the dimension is a prime number, which we call it P, then we have a actual inequality such that so the sum of those two zero norms, sum of zero norm for F and zero norm of its Fourier transform is greater than or equal to P plus 1. All right, so actually the second one is what we will use more in this talk. Okay, so so using those two, we actually want to describe the rank of the gramming based on the zero norm of the generator vector G, right, based on how sparse it is. So we can look at when the zero norm of G is really small. So if we have a unit vector G whose zero norm is equal to 2, so that means we have two non-zero entries in there, then the rank of the gramming is among these 5 numbers. It's either 3D, 3D minus 1, 2D, 3 or 2D, or D. Okay. So actually, these based on this dimension D and some other factors. Okay. So supposedly, if we assume that the zeros and kappas, the entry of G is not 0, right, for some kappa non-zero, then we look at 2 cases. When the dimension is odd, then of course plus and minus kappa are non-zero. So we can conclude that the zero norm of the Fourier transform for WL is equal to D for L equals to 0 and plus or minus kappa. Okay. So in that case, the rank of G is 3D. This actually tells us more when we ask a different question later. So when we limit ourselves on that the dimension is the prime number, then of course most of the time they are odd, right? So I'll talk about that later in more detail. And when D is even, then we do have more cases because now kappa can equal to negative kappa in Z of D. Right? So depend on whether they are equal, and because there is one real number negative 1 among all the roots of unities, in the D's root of unities. So there are different possibilities. So when kappa is not equal to D over 2, then the rank can be 3D or 3D minus 1. And if kappa is equal to D over 2, then the rank can be D, 2D, or 3 over 2D. 3 over 2 times D. So this is when we have a generator whose zero norm is really small. Then what would happen if the zero norm of G is relatively large? So we notice that if D is an odd prime, okay, then if we have if the support, right, if the cardinality of support, or in other words, zero norm of G is greater than D over 2, then we know that the rank of G is greater than or equal to 2D. Okay. So to prove that, we do it by contradiction, right? And now we assume that the rank of the Gramian is between D and 2D. Okay. So since the zero norm of G is greater than 2D, now the WLs are not zero for this G, right? Because if that's the case, we cannot have, right? Because all the translations are bound to overlap if the zero norm of G is larger than half of the dimension D. Okay? So if that happens, then the Fourier transform of WL, of course, is non-zero for all L. Right? And since we assume that the rank of the Gramian, which is equal to the sum of the zero norm of the Fourier transform for WLs, then by the Pigeon's cage, right, there exists at least one L such that the zero norm of the Fourier transform for WL is equal to 1. So that means this WL is proportional to one of the rows of our DFT. Right? So we call it 1 omega to the k and up to omega to the d minus 1 times k. So that actually, if you go back from there and compute the G, then all the possible G's can be obtained by either multiplicative translation or quadratic transformation from this this constant times this vector where all the entries are equal to 1. But these give us a Gramian of rank D, which is a contradiction of with our assumption. Okay, so that means, right, if supposedly we're having a odd prime dimension, if the zero norm of G is small, then the rank of the Gramian actually cannot be small. But if the zero norm G is large enough, the rank of the Gramian is also not that small. So we wonder, right, we have this question, so if we have a odd prime D, does there exist a generator such that the rank of the Gramian is between D and 2D? We haven't been able to answer this question yet, but we do know that if that is ever to happen, right, then the number of WKs, which is equal to 0, has to be greater than d over 3. Right? So because right, since we just proved that, right, if this is ever going to happen, then the zero norm of WK, which is less than or equal to zero norm of G, is definitely less than d over 2. Right? So that means for each WK which is non-zero, we can find at least one entry I such that the ith entry of WK is not 0, but the 2 that's after it is equal to 0. So if we know that, and without loss of generality, right, because we can do translations on the G, which doesn't change the rank of the Gramian, we can assume that this I is equal to d minus 3. So the polynomial with the i's entry times x to the i's have degree d minus 1. So it has at most d minus 3 roots, right, which tells us there exists at least 3 omega to the j's, such that they are not the root of P of k. Right? So that tells us, right, for each WK is not 0, we have at least 3 entries in that WK, which is non-zero. And using that fact and the fact that the rank of Gramian is less than 2D, we can conclude that the number of WKs who are 0 has to be greater than d over 3. Okay. So this is what we can characterize in general about the rank of the Gramian and the sparsity of the vector itself. Next, I'll give some examples that have some interesting relations with our result and something else. Okay, so first we want to look at some specific dimensions. Right? So we look at dimension 4 and dimension 5. When we are in dimension 4, right, we have completely characterized when the zero norm of G is 1 and 2. So these are the first 2 cases. Now, when the zero norm of G is equal to 3, then we know that the rank of the Gramian is equal to 15 or 16. So that is almost, that is very close to informationally complete, right? So when the rank is 16, we do have informationally complete. And when we have 15, we have 1 0 eigenvalues. Okay. So when C is in C5, right, that means it's dimension 5, we can see that when the zero norm of G is 1 and 2, we have the rank of the Gramian equal to 5 and 15. And when the zero norm of G is equal to 3, then the rank of G is also relatively large. It's equal to either 21, 23, or 25, where 25 is the rank of the informationally complete POEMs. Okay. So I won't go into details on the proof because of time. So the first two cases are also came from the earlier result. And for the case that the zero norm equal to 3, we get this these conclusions from the uncertain inequalities, because 5 is the prime number. And in addition, we actually can characterize what exactly generator G looks like when we have rank 21, 23, or 25. Okay. All right. So you might notice that we stopped at 3 and didn't do when the zero norm of G is equal to 4 and 5. That's because things get more tricky when we do have more non-zero entries in our generator G. Okay, so there are many different possibilities to consider, which makes things difficult to characterize. So in order to see that what actually happens when we have a generator vector G with higher zero norm in odd prime dimensions, we actually also look at some interesting sequences. So one of them is autop sequence. So for those who are familiar, autop sequence are actually Kang sequence, which is another interesting topic to research with. But basically, Kang sequence are, we can see them as this type of generators G, whose inner product with its translations are equal to 0. Okay. So autop sequence is one of those. And so if we look at the sequence in a prime dimension, which is larger than 5, then, and we define the J's entry of the vector equal to a cubic power of the phase, which is, so here omega is the fifth root of unity. Then we have that the inner products or the angles between G and GKL has two different values where KL is not equal to 0. So it's equal to 1 over square root of D when K is not 0, and it's equal to 0 when K is equal to 0. So in this case, the rank of the gramming is equal to D squared minus D plus 1, right? Which is actually which is actually a large number, right, comparing to D. And we only have two different actually three different eigenvalues. Okay. And another example that I want to mention is another Kang sequence, which is the Bjork sequence that is defined using the Legendre symbol. So I put this both here just for the sake of completion, but let's look at when the dimension is prime and it's equal to 3 mod 4. Then we define the Bjork sequence, which is equal to 1 over square root of P at when K is equal to 0, and it's a quadratic residue of P, and everywhere else it's equal to a phase times 1 over root of P. And for this Bjork sequence, right, we know that we have P plus 1 different eigenvalues for the gramming G, and the rank of G is less than or equal to P squared minus 2P plus 2. Right. For here, I want to say it's equal, but I haven't found a concrete proof for that. So to prove that, I think it's related to the Klusterman sum, and I personally don't know too much about it. So if you are familiar with that, please let me know. Okay. And we have actually interesting loop right here in the eigenvalues, that if k times L is equal to k prime times L prime mod D. Sorry, this is a typo here. It should be mod P, which is the same with the dimension it is in. So if these two are the same, then the inner product between, or the absolute value of inner product between G and GKL is equal to the absolute value of the inner product between G and G of K prime L prime. And to show that what it looks like, so this should be G, the absolute value of inner product between G and G of KL. And we can see that it's repeating. This value is repeating in each row. Okay. Okay. Right. So this is what I want to talk about today, and here are some reference. This is our articles on this talk, which will be on archive really soon. We are finishing it up right now. Okay, and okay, that is all. Thank you for your attention. And
thank you very much for a nice talk. Please, some questions and comments. Okay, maybe I will start with a question. On the first slide, when you give the definition of the frames, you have there the constant, the multiplier n over d. It was one of the first or second slides, I think.
The second slide. Is this one?
No, the previous one, probably. Maybe. Yeah, here. Like in the definition of FIO and TF, did you try to consider also frames with some, when you put some additional multiplier instead of n over d, maybe some additional constant, or because like actually like frames like when there exist like two constant from above and below, right?
So in general, right, for type frames, we do not know exactly what this constant is. So it can be some other number, but if we are only looking at finite, we are looking at unit norm type frames, then we actually know what this constant terms, which is equal to n over d. And you can get this result, I believe, from the frame potential and some other ways.
So I guess the question is whether or not you could prove, you could sort of extend the result for when you just have a frame, not a tight frame.
Yeah, I was missing this tight frame.
So yes, so I think the correspondence that she put between like tight frame and POVM, that you lose that because the definition of tight frame that she gave is essentially equivalent to like a resolution of the identity. Mm-hmm. And if you don't have that, then your POVM will not be rank 1 of a form that she's sort of defining down here, and that way you sort of lose something.
Mm-hmm. Okay, I understand. Thank you.
But it's also true that for any frame, you can always canonically associate to every frame like a tight frame. So it's not going to be a unit norm. and the constant is just going to be the sum of the length of each of the vector that you have. And with that, you can still do the same association, except that it will probably not sort of be like as clean as what's here, in the sense that here, not only she specialized to this kind of tight frame, but she also went further down by looking at only Gabo frame. And Gabo frame, we know for sure that they're always tight. So that's a definite difference.
Yeah, that was what I was trying to comment on, because you'll see, like from here, I think everything is about Gabor frames, and we know that finite Gabor frames are all tight frames. Right?
Okay, I understand. Thank you. Please, some other questions, comments?
So actually, yeah, my question also is based off of this slide. And maybe you said this during the talk and I just missed when it happened. So you have that rank 1 POVMs correspond to tight frames, but you gave plenty of examples where we were looking at POVMs that had a wide variety of different ranks. Do you know if the POVMs of like certain other ranks correspond to specific other well-known mathematical objects? Like, does a rank 2 POVM correspond to something?
I don't think I have. I know any of those, because
maybe if I can help a little bit. So Ryan, I think there is how do I call it? So we use the notion of rank in many different places. All the POVM that we dealt with in this presentation are all rank 1, because they are generated exactly like by just like taking a Gabo vector and taking multiplying by its conjugate, just a rank 1 generated by that. The rank that we're talking about is actually like the rank of a matrix, or if you view like those collection of vectors of matrices inside in the set of D by D matrix, we're trying to sort of see what the dimension of a vector space that these things span.
Okay.
That's the difference between this and that. So
okay,
we only consider rank 1, but we're looking at this in the set of matrices. And when it's complete, it's exactly when it forms a basis for this set of matrices. When it's incomplete, then we're trying to sort of see what the dimension of the subspace that they span. That's what
I see. Thank you. Yeah, I definitely had a little misunderstanding there.
On the other hand, your question is well warranted, because yes, there are over kind of there are POVM that are non-rank 1. So for instance, I think like there is a recent paper by, not too recent, but by Dustin and Joey Iverson, where they look at I believe rank 2 or rank 3 POVMs, and they use them to actually consider like equiangular tight frame. But the equiangular tight frame that they get are not the one that you consider usually. Like, so in that equiangular tight frame in CD, you technically you can find them for a number of vectors that are between D plus 1 and D square. And D square is exactly the case of the Zauner conjecture. So what we're dealing with are things that are somehow like in between D plus 1 and D square. So they use some rank 2 or rank 3 vector, rank 3 matrices to actually generate those kind of POVM.
Okay. Thanks.
Yeah, thanks, Casa. Yeah, I actually was always confused by this terminology. The SIGPOVM stuff. Yeah, it actually explains it well. Thank you. Yeah.
Yeah. And the particularity here is that Shujie mentioned this briefly. When you have, if you go back to the definition of a symmetric part, so go to the symmetric, once the thing is symmetric, then it's automatically information complete, because by symmetry, you can diagonalize this thing using the DFT matrix. And so you know that this is going to sort of have like, be like linearly independent. So if you're dealing with a Gabo system, the notion of symmetry is exactly the same as informational complete in a certain sense. But in general, these two things are not the same. So
can I comment one thing?
Yeah, please. Yeah.
Yeah, so So actually, right, the symmetry, so if you want the symmetry to imply informationally complete, I think you need to specify the number of vectors you have, like that's in, right, or else you don't have the equivalence here, right? If you don't have
Right, you
enough,
could have just two vectors, and
Yeah.
technically that could be symmetric.
Exactly.
Okay, yeah, I see what you're saying. Yeah, thank you for thank you for commenting that.
Please, some other questions or remarks? Okay, when there is no more questions, maybe we can stop the recording and maybe somebody else, and let's send